So the warning here is I'm presenting somebody else's slides and somebody else's work. So we'll see how well I do. So basically, I will do my best to answer any questions about this. I have worked on cavities a long time ago when I was an undergrad. So if you have questions I can't answer, Katerina can answer your questions offline. But like I said, I'll do my best. All right, so to start, I think that, oh, here, let me see if I can, is there a way to get rid of this? It's fine. Okay, so I think this is basically just showing that hunting axions is now really a worldwide affair. And actually this map I was realizing is actually out of date. There's more axion efforts now. So for example, this doesn't show anything in California, which of course I care a lot about. But yeah, there's lots of various people looking for axions. This is both the dark matter searches and the other kinds of searches like light shining through walls and solar axion experiments, which we didn't get to on Monday. But you can see many people are now interested in axions. Okay, so you talked about this a few different times with the various folks. But once again, basically saying that there are several different interactions you can look for, axions interacting with photons, with nucleons, spins, all different kinds of things. And in particular, you should be thinking about the fact that they're pseudoscalars when you're thinking about how they're interacting versus our dark photons that we talked about before, which are vectors. Okay. And then, but the thing is, like we talked about before, all of these coupling constants are inversely proportional to this very large energy scale that you learned about yesterday from Marco when you have PQ symmetry breaking. So these are all really small interactions. And that interaction is also proportional to the axion mass. And that's why we have this diagonal line for this QCD axion. So it goes down as you go to lower masses. Unless you're looking for ALPS, in which case, again, it's a free parameter. Okay, so the nice thing about this plot is it actually divides the space. So you can see here where there's a bunch of these sort of cavity experiments, and then down here you can see lumped elements. And again, this is a little bit outdated because it doesn't show some of the projections for some of these new ideas for high mass detection. Okay, and here's just pointing out that a very large fraction of these searches that are looking for axions are actually looking for axion dark matter. These are the sort of most sensitive searches that you can do if you're trying to reach all the way down to the QCD band. So this lecture is going to be talking to you about cavities, which are in this sort of micro EV range. And yes, so basically cavities in this mass range are the most sensitive kind of experiment. And really, so far, they're the most sensitive kind of experiment in any mass range because they're the only ones that have actually reached down to the bottom of the QCD band. Okay, so you've seen this kind of thing before. Oh, you want to? Yeah. She may also be willing to share the slides. I don't know, but you can ask. Okay, so we've been talking about this the whole week, right? That we have wave-like dark matter way down at the bottom end of the mass range that we do physics with. But I really like this sort of sketch that she included in her slides just to show how much lower we are than all of the other pieces of physics. So if you think about we're looking for axions, we're high energy physicists, but most high energy physicists are living all the way up here when you're talking about really small length scales, really high masses. And then there's also sort of nuclear physics, atomic physics, and condensed matter, all at higher energies than we are doing when we're looking for axions. And so we really need to be thinking in terms of waves instead of particles. And we can actually do these kinds of experiments because these are coherent classical waves that we're looking for, rather than just looking for individual particles with energies that are 10 to the minus 22 electron volts. Oh, and I think one note is the experiment that Katerina works on, Quacks, is looking more in the sort of 10 gigahertz range. So we're talking about tens of micro EV. Okay, so what are the actual observables in a dark matter search? Well, this is that sort of Maxwell-Boltzmann distribution that we talked about before. All of this is now in terms of actually the velocity of the dark matter itself, and you're basically seeing the distribution of those dark matter masses. And you have to keep in mind that you are taking account for both the motion of the sun around the galaxy and the motion of the individual dark matter particles in the cloud. I'm not sure what we're trying to get away from this. I think that may just be, yeah, describing how you get those curves out. Yeah. Okay, so once again, we're now talking about this cavity regime and that sort of middle masses where you have the dimensions of your experiment are on the sort of meter scale, the person size scale. So for a 10 gigahertz experiment, we're looking for these sort of 40 micro EV axions, but the de Broglie wavelength is going to be longer than that because you have to take into account this velocity. So the non-speed of light velocity. And so you end up with a de Broglie wavelength that's 70 meters. And so that tells you how long you're going to be coherent for. As the sun is, or as the Earth is traveling sort of 70 meters, that's how long your signal is going to be coherent. And then once again, we're talking about very high occupation numbers. So in this mass range, we're talking about something like 10 to the 25. And so you can, again, look for it as a classical field. Okay, so yes, as your detector is traveling 70 meters. When you think about that in terms of 220 kilometers per second, that means you have about a 200 microsecond coherence time. And you can compare that when I was talking about DM radio gut. Right at the bottom end of that DM radio gut frequency range, we were talking about something like 10 seconds of coherence time versus this 200 microseconds. Higher frequency, we still have that 10 to the 6 oscillation before we go out of phase, but now we're at a shorter time scale. So this is nice in theory because it means you can integrate for less time at each band. But again, we're still looking for the sort of delta F over F of 10 to the minus 6. So, okay. So, and that's basically what's right here. We're talking about the quality factor of 10 to the 6. Okay, so then if you take this distribution of velocities, then you get out this distribution that I showed you before, which is the sort of power with respect to frequency. And so when you're actually trying to calibrate your experiment and make sure that you're doing things correctly, you want to inject a signal that looks like the axion. So you inject something that in frequency space looks like this, but you want to do it in the time domain, and so you get something that looks kind of funny like that. And so that's what you're actually injecting when you're actually running the experiment. Okay, and so now we're going to get more into like how the cavities actually operate. And this is a nice toy model to explain this. You can think about it basically as sort of these two mirrors that you're going to have some sort of wave in between. Again, those mirrors are defining the boundary conditions for your wave. So if you think about putting sort of something metal in a field, you're going to have this boundary condition that is enforced, where the electric field has to go to 0 at the boundaries. Okay, and so then you can think about all the different modes that fit inside that cavity. The first one just looks like this. You can also have sort of the full sine wave in there, et cetera, et cetera. This is a classic thing you learned in undergrad. You can write out the different modes this way, and then of course they're also going to oscillate in time. And so this looks kind of like a drum, right? It'll be beating up and down. And the way that you actually generate the signal inside your detector is by filling this cavity with magnetic field. And then you end up with the E field oscillating parallel to it because of the axion interactions. Okay, yes. So this particular setup, though, is only going to allow you to look for one axion, which has a wavelength that is double the size here, right? If you think about sort of the other, you can only look for one with this mode, but you can also look, if you had, say, the mode that looks like this, you could also look for axions with that frequency. All of those possible modes are something that you could look for in that cavity. But keep in mind, right, the mode that looks like this is not going to give you any sensitivity because you have a cancellation, right? The E field is going in opposite directions. So that will cancel out your total signal. I think there's more slides on that later if folks are confused, but ask me again later if that's confusing. Okay, so if you want to tune over a wider range of masses, though, you basically need to find a way of changing the spacing between these mirrors, or else you are limited. Okay, so this is what this looks like in real life. It's not just two mirrors. It's actually a cylindrical cavity is the classic way of designing this. So once again, there's your interaction. in your cavity, you have magnetic fields pointing in the z direction, and then when the axion interacts, you're going to get that electric field that's going to set up inside that cavity. Sort of a standard size of cavity is going to be able to give you something that is in the sort of gigahertz to tens of gigahertz. Okay, what is the actual power, though, that you can get out of this cavity? Well, it depends on a few different things. The stuff in gray is the stuff that you don't control. Again, that's the axion physics. So we have the coupling constant, the local dark matter density, and the axion mass. And then all these colored bits are the parts that you can control. So just like we saw for the lumped element experiments, you have the strength of the magnetic field squared that will enhance your signal size, the volume of your cavity, and the quality factor of your cavity. All of those things are going to enhance your signal. And then you have this thing, which is new. This is a form factor, the CMNL. This is very similar to that CPU that I told you about for lumped element cavities. It's basically saying, so for lumped element cavities, you could think of CPU as how well coupled the axion signal was into your pickup. This is basically saying, what is the overlap between the axion signal, which is fully distributed in the magnetic field, and the mode of your cavity. So this is this sort of electric field distribution. Yes? Mm-hmm. Yes. Yeah. And there will be some more pictures of modes later on that you'll get to see what that actually looks like. But that's exactly right. Yeah, I think this is actually, maybe it's on the next slide. No, it's not on the next slide. There will be a description of how we actually calculate these form factors a little bit later on. So ask me again when we get to that slide. Any other questions here? Does this sort of basic concept for cavities make sense? Okay. Yeah. That's a great question. And so I'm going to sort of put that back on the group. What do we think about that? And this ties back to that question where I asked about if the toroid or the solenoid could be used for dark photons and the differences between axions and photons. So what is the direction, though? What is the direction of the axion, though? No, like fundamentally, what is the direction? What does it mean for the axion to have a direction? Yeah. So we do have like a preferred direction for the wind as the Earth goes through, but that velocity is like pretty small. So if you think about the width of that axion signal, it's really narrow. It's 10 to the minus 6. So you can think of it as almost not having a direction, at least for the case of cavities. And because it's a pseudoscalar, there's no preferred direction for the field itself. So it actually doesn't matter what direction the wind comes in. You're just relying on the fact that there are axions inside your cavity. And then that additional velocity is going to change what the energy of the photon is that comes out. But it's not because it is sort of stochastic, there's not really a preferred direction in this thing. Now, I will tell you when we get to those high mass axion searches, we actually can see it to some extent, but it's a small effect. This one, you can't tell what the direction of the wind is coming in. For dark photon, that's not true, though, because the photons themselves have a preferred direction. They have some sort of polarization, right? And so then you do have to have this alignment. And so if the dark photons are sort of randomly distributed, there will be some sort of net polarization, but they could all be polarized in some specific direction because of some, like how they're formed or whatever. And then you really want to think about how you're aligning your cavity with that polarization. Does that make sense? So that being said, if we're doing these other kinds of searches, which again, I wish I had gotten a chance to talk about it earlier, but the axions that are coming from the sun or that are being generated in the lab are typically being generated at much higher energies. And so that velocity vector really starts to matter. because then you're really highly not conserving momentum, and that starts to be a problem unless you line things up. Yeah. Does anybody have any other questions on that topic? Yeah. So, like I said, there is a preferred direction if there's a wind, but then if you ignore them, like our reference frame, and just think about the galaxy, it's just a virialized halo. So they've sort of been collected gravitationally into the galaxy, but there's no, unless you're thinking about like a dark matter stream, in which case, sure, yeah, they're all moving in a direction because they're sort of entering the galaxy. The rest of the dark matter halo is just virialized. Do you have a better explanation? Yeah.
Are randomly oriented in the galaxy, but you usually have a different directions. They get a direction. There is an order one because the virial velocity is roughly also the velocity of the sun. Essentially, in order one is something. So there is a preferred direction. It's just.
So one way to think about this is, so the dark matter halo is, you can think of it as roughly like a spherical distribution because there's less interaction. So the reason that the galaxy is in a plane is because visible matter interacts so much that it has formed this disk, whereas the dark matter is not interacting so much that it has collected into this disk that is rotating together. Does that make sense? Roughly, yeah.
So they move with random directions. They don't carry angular momentum, right? So the galaxy is like this, and it's all rotating. Well, it's mostly rotating in one direction. They're moving in all directions.
They've been gravitationally bound, but they have not picked, some net angular momentum. Other questions here? These are really good questions. Okay. Okay, so like I said, we'll get back to form factor and how we can actually calculate that and understand what this overlap really means. But this, just like CPU, can only go up to 1, right? You could have maximal overlap where E and B are perfectly overlapped, so you can't do better than that. So thinking about what you can actually have here, this is so small that the actual power you're measuring is exceedingly small. So 10 to the minus 23 watts. This is like ridiculously small amount of power to be measuring. I think I'd seen some slides at one point where somebody compared this to if like one of the Voyager missions, like they're releasing like 1 photon every certain amount of time, and it's like less than that. So really, really tiny amounts of power. Okay, so then what are the ingredients that you need for a cavity experiment? And these you'll see map onto those 3 ingredients I told you for all dark matter experiment, or all axion experiments. So the first thing you need is you need some kind of resonator, which is your cavity. So you can, she says, basically think about it like a harmonic oscillator driven by an external force. So basically the axion is driving your cavity to oscillate, but it needs to be tunable so that you can match the axion mass. And then you need some way to actually cause this drive, which is you basically take this cavity and you put it inside a very large magnetic field. So many Tesla often. And then you still have this very small signal, and so you read it out with some very, very low noise receiver. And as we'll talk about later, this is often done with superconducting electronics. So the signal to noise ratio is set by how strong you can make your signal, which is the magnetic field, how much you can enhance it, which is how good of a cavity you can make, how much signal you are actually putting in the first place, which is the coupling, and then the amount of noise you get is set by the receiver. Okay, and so here are some really nice photos of what this actually looks like in real life. It's not just a cavity and magnetic field. There's lots of infrastructure involved. I can't point out all of the details here because I haven't actually been there, but basically I believe this is the cavity that gets inserted into, and you can see it hanging here, that will get inserted into this larger magnetic field, and then all of that has to be supported by this cryogenic infrastructure, which is all of the stuff you're seeing here. Okay, so here we're getting back to that form factor question. So how do we actually calculate this form factor? Well, we're basically doing an integral of the electric fields of that mode dotted with the magnetic field that cavity is being placed inside. And so do y'all know the language of TE and TEM modes? These are transverse electric and transverse magnetic. Okay, great. So basically, when you have a transverse magnetic mode, the magnetic fields are going to be in the plane. Transverse electric, the electric fields will be in the plane, and then TEM, they're both in the plane. But we know that our magnetic field is pointed in the z direction. So anytime you have your transverse, your electric fields that are transverse, they are not going to be contributing to your signal. So you can immediately cross out this one and this one as bad ideas if you're trying to look for axion dark matter. And so you want to use these TM modes. And so if you actually do the full calculation, you can see you do this integral where you dot them together, and then you normalize it by the strength of your magnetic field and the strength of the resulting electric field. And then once again, you can never do better than 1, but you can do 0. These would give you a 0 form factor, and then you would just have no sensitivity. So most of the cavity experiments use this TM010 mode, where you're using, basically you just have a half wavelength inside your cavity. That typically is going to maximize, sorry, is there something you, okay. Okay. So yeah, so most cavity experiments use this TM010 mode, where you have a half wavelength that fits inside your cavity, because that is typically going to give you the largest form factor. But you don't always have to do that. And if you're trying to reach higher masses, it may make sense to use some of these other form factors, because then you can use a larger cavity and still get to higher frequencies, right? Then you don't have to sort of really shrink your literal volume, although again, using these higher order modes will shrink this, this form factor. Did that answer the question that you were asking before? So that's more like the SRF cavity heterodyne detection, where you're going from one mode in your cavity to another mode in your cavity. This is really, you're not exciting from another mode, you're just exciting one mode. So you're going just from the axion field into the mode of your cavity. So the magnetic field that's distributed inside your cavity isn't really a mode, because it's just filled homogeneously. Does that make sense? Yeah, it's going from no mode, because let me see if I can draw this. I don't know, can you see here, or is there people over there blocked? Can you see within that space? Okay, great. So the magnetic field is fully filling this space, right? So there's no like boundary conditions that are being enforced. That's what I think of when I think of mode, is there some boundary conditions that are enforcing some wave structure on here. So this is just, you can think of, if this is the magnetic field, this is also the axion effective current that we talked about, fully filling it. And then sometimes through, which is determined by that Ga gamma coupling, you will have an axion convert into photons, which have to follow this restriction. So you're basically loading that mode with photons. Yes. Well, I mean, it's because we're in this sort of RF cavity regime, the TM modes also have an associated magnetic field, but that magnetic field is like this, right? Following that first column. Right, because we're using the E dot B coupling. So that's how we determine how much the cavity can actually be loaded. Now, the photons that have this electric field just also have this associated magnetic field with them. Make sense? Yes. Yeah. You can think of it as it's a harmonic resonator, so you can just keep loading it with more and more photons. And so you're going from 0 occupation to 1 occupation to 2 occupation. Okay, great. More questions here. Does this make sense? Yeah. So there's no generating electric field. There's only generating magnetic field. Like the magnetic field is causing the generation, but the result maybe you're asking about the result. So basically, this is the electric field, and so is that what you're asking? And then, yeah, and then the magnetic field goes around like that because they have to be perpendicular. Other questions here? Yeah, the mode is a property of the cavity, but whether that mode is occupied with photons or not is what we're asking here. So if you don't have axions, the mode will not be occupied with photons. But if you don't have a mode, if you didn't have TM modes for some reason in your cavity, you would just not be, the axions would not be able to generate photons into your cavity. At least not resonantly, right? You just have like maybe random photons that are being generated, but they wouldn't have any sort of enhancement. They would just be a photon that would go away. Yeah. Mm-hmm. Yes. So the power that's being dumped is what we saw just a couple slides ago. And that's just here. So this is the power of axions going into photons just continuously. It doesn't, because it's a harmonic oscillator, there's no restrictions on how much you load it. Right. Yeah. The electric field is purely generated by the photons that are loading it. And you can just keep dumping power and increasing the amplitude. You're talking about this? Yeah. Yes. 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 Yeah, so in the first talk, I was trying to emphasize when I showed you that plot that all of those different blobs use different assumptions, different sources. All of the dark matter lines on there assume that axions are all of the dark matter density. So that's a different systematic you get when you have a dark matter exclusion versus an astrophysical exclusion. The other thing that's hidden under the hood, right, is we're assuming that axions are all of the dark matter, but you also have to make an assumption for what the local dark matter density actually is. And so because of historical reasons, most of those exclusions use 0.45 GeV per centimeters cubed, which we actually think is probably not right anymore. It's probably more like 0.3 or 0.4 GeV per centimeters cubed. And so you have to correspondingly in your head shift those exclusions up and down based on what you think the local dark matter density is. And then another thing to think about is that number of 0.3 or 0.4 GeV per centimeters cubed is determined not by measurements that we're actually making on Earth. We can't make measurements of the dark matter density actually on Earth. We're using an estimate based on star motion, which is like in our sort of local region of our galaxy, right? So we could be living in an underdensity, and that would really suck for these kinds of experiments. Or we could be living in an overdensity. Maybe we'll get lucky, right? But we just don't know. And so that is an assumption that you make when you write those lines down. Yeah. Other questions on that? Okay. All right, so we're going to be using these TM modes, and we're going to be using the different modes depending on what mass of axion you're going to be looking for. And so the take home here is that all of these, so this cavity has a bunch of different modes. That's just a property of the cavity, but only the ones that have these electric fields that are parallel to the magnetic field you put them in will actually resonate when exposed to the axion field. Okay, and so here you can see some more pictures of what this actually looks like in simulation. Anytime you're making these kinds of experiments, you're going to be running lots and lots of electromagnetic simulations to make sure that you know what's going on inside your cavity. And so you can see here's simulations of a bunch of these different modes. Some of them don't work for axion detection, but all of these other ones would. And then I think this is a really nice, maybe easier way to actually understand what's going on. You can see this is the rate, like the radius of your cavity versus the field strength. Here's that TM010 mode that I drew on the board. And then you have these 020 and 030, where you have sort of different wavelengths that fit inside. Okay, yeah, and then this is really nice. You can see, so this is, I don't know if this is too small to see in the back, but this is those different modes, 010, 020, 030, and you can see on the right here what the calculated form factor is, and you can see that it really drops off quite quickly as you go to these higher order modes, going from 0.7 down to 0.05. So you are decreasing the sort of effective volume of your cavity. But again, it allows you to reach higher frequencies. Okay, so you don't just need to know what the signal is, you also need to know what your noise is. You have to really understand the signal to noise ratio in order to determine what your sensitivity is going to be. And so you put this part on the top, and then you have to include this noise figure on the bottom. And so I'm not actually sure what TM is here. I think what we should basically be getting away from this is that we can write this in terms of noise temperature. Do you recognize what this equation is? Yeah, I'm not sure what this equation is supposed to mean. Okay, we'll put a pin in that. If you're really curious, we can send Katerina an email. So the noise on the bottom, so this TN is the noise, like system noise temperature. So you can, and I think this may come up later, but basically you can rewrite all the sources of noise as an effective temperature in your system. And that's a way of classifying everything in the same way. And then you also have to include the bandwidth. I think that's what this B is, the bandwidth over which you're searching in. So maybe we revisit this if it becomes relevant. Okay, so let's talk about scan speed at the different frequencies. So that may be correct.
Oh no, but it goes like the fourth width of time, but PA goes like square of the time.
Yeah. I think that's correct. Yeah. So this is, I guess, this is the signal to noise if you're only measuring coherently. As you go beyond that 200 microseconds of coherent integration, then it'll start going as the fourth root of time.
G goes like G squared, so actually G goes like fourth root of time.
Okay. So this is past that. So okay, there's a bunch of stuff under the hood here.
This ratio of signal to noise for these parameters, the amount of time you can be.
Great. Thank you. We'll go with that. Okay, so the signal to noise is an input when you're trying to figure out how fast you can scan, right? Because I think I showed you in the scan rate yesterday, basically, it's 1 over the SNR squared is one of the inputs to the scan rate you're looking at. So it's harder to reach lower masses in that you have to ring up your resonator longer and the GA gamma gamma line falls. But you also have to take into account with a cavity search that the size of your experiment is reducing as you go up to those higher axion masses. And so you actually have sort of a difficult scaling as you go up to these higher frequencies, because if you're continuing to use a cavity, that volume will fall. And so you end up having, again, an unfavorable scaling as you go up. Another thing to note is that we have this pretty wide QCD band. To get to the bottom of it, this is this DFSZ model. You have to scan at, it's even slower than if you're trying to get to the KSVZ by a factor of 50. And we really want to try to probe that entire band. We don't want to just go to KSVZ and call it done, because what if your axion is sitting just below your sensitivity? So yeah, you can see here, basically, this is the difference between scanning at 100 megahertz per year or 2 megahertz per year. So it's a pretty big difference when you're talking about trying to get a PhD or something like that, right? Okay, so the problem is scanning at these sort of rates, you cannot scan this full range until you have like 100 years of integration time, right? So this sort of most simple method where you're looking at sort of basic quantities, that's not going to be enough to actually probe this full band. And so you have to figure out how to improve your technology so that you can scan faster. Okay, so Yes. So basically, because you have these like really high powers, if you want to actually double the sensitivity to Ga gamma gamma, you're going to need to improve the rest of your parameters by a lot, which is really unfortunate. So here's some photos. I think this is all of quacks. Of actually what a cavity looks like. And so basically what you do in order to tune the size of your cavity is you don't just actually physically change the size of your cavity, because that would require swapping things out, warming up, whatever. You basically have some sort of tuning rod inside your cavity, and that changes the mode structure inside. And so you can see this is what that physically looks like. This is the outer walls of a cylindrical cavity with a large tuning rod inside, and then you can simulate the modes sort of as this tuning rod moves around. You still get that same structure. And then this is sort of a top-down view of what those modes look like. Red marks where you have regions of high electric field, blue is regions of low electric field, and you can basically see that the size of this red spot is changing as you move that cylinder around, and that means that the size of that mode is changing. Okay, and so I guess for quacks, their goal is to be able to scan KSVZ at 40 megahertz per year. Okay. Okay, an additional challenge to these cavities is that, okay, you have this mode structure for your TM modes, but you also have all of these other modes. And when they get close to each other in frequency, they hybridize. So they start to mix with each other. And so you get this really annoying behavior where instead of having something that looks like this, as it gets close to this TE mode, you're going to have something like this. And this is really going to destroy your sensitivity. And it's going to be really challenging to figure out what your sensitivity is. So when you make a plot of the different modes, this is the position of a tuning rod versus the frequency of your mode. All of these lines are different modes inside your cavity. And anytime the lines get close to each other, you cannot make an axion measurement. And so you basically extract that frequency range out of your sensitivity band. And so I think you can sort of see it's maybe a little too zoomed out, but you can kind of see how there's these sort of fingers going down. If you were to really zoom into these results, you would see that there's lots of cuts out of every single cavity experiment. Those are places where they lose sensitivity for whatever reason. A lot of those times it's because of these mode crossings. Sometimes it may be because they have a source of electromagnetic noise also that they just veto out. Okay, so there's different ways that you can design these tuning rods. You can use either a conductor or you can use a dielectric. Quacks uses a dielectrically loaded copper cavity. So instead of having a copper tuning rod, they have a sapphire tuning rod. Sapphire is a really nice material for these kinds of searches because it has really low loss. And so you're not going to be totally destroying your quality factor by adding this dielectric into the cavity. And so you can see here are the different modes. Actually, I think this is all TM030 so that they can reach higher masses. Part of the point of quacks, as you can see again on this plot, is to reach up to some of these higher axion masses. Oh. Okay, yes, and so using this dielectric tuning rod, because remember before when we were looking at the form factor for that 030 mode, and we saw that the form factor was only 0.05, by using a dielectric, they're actually able to increase this form factor. One of the things about dielectrics is they kind of like suck electromagnetic modes into them, and so that can help you maintain your high quality factor. At least that's my understanding of it. So you can see here is, I think this is maybe the position. Okay, this is where you have negative contribution to your signal, and these other places is where you have positive contribution. So yes, there is going to be some cancellation of your signal, but as a whole, you're going to have net positive contribution. And I'm not actually sure what this clamshell mechanism is. Do you know what this clamshell mechanism is? Okay. A question for Katerina if you're curious. Okay, and so there's some really nice photos of what this actually looks like. You can see all of this very beautiful copper. It's really critical at these frequencies that you make sure you have very smooth surfaces and you don't have sharp corners, because those are places where field can sort of collect and then you lose, again, your sensitivity. You want it to have it be distributed across your magnetic field. And you can see they have this way, I had to look up what this pantograph is. It's really cool. It was designed a long time ago. It's a way to like draw certain kinds of geometric figures, but basically this shape can, this is a hinge, and so this can go up and down in a sort of very smooth way. Perhaps it does. I would not expect the cavity to actually be opening itself, because then you would start to have loss outside the cavity. Okay, great. Thank you. Yeah, you can see it on the outside here. So yeah, maybe that's correct. Maybe they actually change like the position of part of the outside of the cavity. You'd have some leakage. So it may be it looks like this may be a flexible material here. So maybe they're actually changing the sort of shape of that material. If you find it, we should.
It seems like it's both. So I think it's the same mechanism.
Okay. Okay, well, once the Googling is done, we'll review clamshell. Mm-hmm. Yeah, maybe. We'll see. Other questions about sort of what you see in these photos? I think it's nice to have actual photos of experiments, because some things are sort of hidden in there that you don't see when you're just looking at simulations. Okay. Okay, so that's all the part about the cavity. That's about trying to generate as much power as possible. The other piece that's very critically important is reducing the denominator, so reducing the noise. And the way you do that is with ultra low noise receivers, and these are often based on superconducting circuits. I believe Quax uses TUPAs, which are traveling wave parametric amplifiers. Other cavity experiments have used JPAs, or Josephson parametric amplifiers. People have historically used squids and other things. And we'll talk a little bit about how parametric amplification actually works. So here are some nice photos of some of these devices. But basically, what you need is you need some sort of like pumping and nonlinearity, and you can get this with Josephson junctions. And actually, we'll talk more about this when I'm talking about low noise quantum sensors as well. But there's a lot of things that go into this. This is an entire other field that we're basically importing the results of their field for use for axion detection. So designing these circuits, you need to be thinking about circuit QED, cavity QED. There's lots of like Hamiltonians that you're going to be writing down as you're figuring out how signals are propagating through the system. You need to be figuring out how to nanofabricate this. So that's one of the big challenges, is actually how you can fabricate these circuits. And then, of course, you also have to integrate them into your experiment, which is an additional challenge, because oftentimes the folks that are designing these circuits are not thinking about connecting it to this macroscopic cavity or macroscopic receiver. They're thinking about designing it for use with something like a qubit system. Okay, so this is a picture of what this actually looks like. So this, I believe, is actually a photo of a dilution refrigerator used for quantum computing. And the reason I think that is because you have a ton of RF lines coming down. The reason you might want that is if you have a ton of qubits in your system. And so all of these lines are going to things down here. It does not necessarily qubits, I'm just speculating, but that seems likely. On the left side here is what it actually looks like when you're building an axion experiment. You just have one receiver and just a few RF lines that are coming down, and then the rest of this is all sort of cryogenic support systems. Okay, how do we actually get cold enough to do this? You have a bunch of different mechanisms that you can use to get to various temperatures. So the thing that we end up using when we're doing a dilution refrigerator is a helium-3, helium-4 mixture. And this allows us to actually get down to 10 millikelvin. And the mechanism here is basically that you have this mixture and you're pumping helium-3 out of helium-4. And that process takes energy out of the system. So it's really, really effective, but it doesn't have a lot of cooling power. And so you can cool only a limited amount of volume down with that procedure. For a long time, and for other things where you don't need to get as cold, you can basically just use helium-4 or helium-3 instead, and that will get you down to a few Kelvin or even sub-Kelvin, but not all the way down to these millikelvin temperatures that you need when you're operating these superconducting circuits. Oh, also this reference here is fantastic, by the way, if you're ever looking for a cryogenic textbook, Pobel, it's great. Okay, so, oh yeah, here's a slide. So basically, this is what I was talking about, where I guess this is the Pioneer probe. 12 billion kilometers from Earth, the signal we're getting is 10 to the minus 21 watts. For dark matter, we're getting something that's orders of magnitude below that. So really, really tiny signals. We have just a few photons per second, and so we need these quantum techniques in order to improve our noise performance. Okay, so before I get into the sensors themselves, this is just pointing out that these are really building on a history of microwave receivers. So you can see back in the 60s, this is really historic microwave receiver. We now have very large scale radio telescopes, which are also building on this history. I believe this is the largest movable object on Earth, or at least it was back when I was an undergrad and I visited this telescope. It is very impressive. It's actually like 2 football field sized telescope that is being moved around. And this is very similar to what we're actually doing for an axion experiment, just on a totally different length scale. It's 100 yards long. I don't know how wide it is. Yard is also the wrong unit, right? It's like about a meter, yeah. So it's yeah. So it's about a football field in size, no matter what football you're playing. Yeah, so this is enormous, super impressive. We don't have to move anything that big, but we have to make it cold instead, which is an entirely different challenge. But it's the same idea where you have this microwave receiver and then you have to read it out in a low noise way. And so I think that's what this is showing down here. This is an axion experiment as compared to a radio telescope. Okay, so as you're reading this out, you're going to need to amplify your signal because it's small. But anytime you add an amplifier, it's going to introduce its own source of noise. And you can think about this as Johnson noise. So basically, it either is literally Johnson noise where it has some temperature, or you can describe it instead as an effective temperature that it's adding. So yeah, so you might be adding literal Johnson noise, and then you might also be adding quantum noise that you can quantify with a noise temperature. You can quantify in terms of Kelvin, watts, number of photons, depending on your preferred unit. I think this is, yeah, kind of a nice, well, yeah, move on. Okay. So if you are trying to actually quantify what the added noise is, this is basically an explanation of noise temperature. So you can either think about it as just the temperature of a resistor, or you can think about it you can think of it as a resistor at a certain temperature with a noiseless amplifier, or you can think of it as a noisy amplifier connected to a 0 temperature resistor. It's an equivalent description, and either way, that is what the equivalent temperature is. Okay, so when you're actually trying to quantify what the noise is in your amplifier, you have to measure it yourself. You're not going to rely on whatever the spec sheet is from whoever is giving you this device. And particularly for these axion experiments, a lot of times you're not going to be getting a spec sheet because it's going to be your friend who's working in quantum computing who's making these amplifiers. And so the way you can actually quantify this is something called a Y factor measurement. And so this is actually a really nice description of how this works. So basically, you take your amplifier. It has these properties, it has its own gain. You're trying to measure what TE is, that equivalent noise temperature. And what you do is you connect its input to a hot load and a cold load. And this is literally something you put at the hot stage of your fridge and the cold stage of your fridge. So you take an attenuator and you put one at 4K and one at 1K, and you can compare the difference between those things. And so you can write out here basically what the contribution is. So this is the contribution of your noise from the hot resistor or the cold resistor, and this is the contribution to your noise from the amplifier itself. And then you can make this, this is the Y factor, this is a ratio of the hot noise to the cold noise, and you can basically do some algebra, and then you can see that you can get out, using these known T1 and T2, you can get out what the effective noise is for your amplifier. And this is one thing that's really nice about these dilution refrigerators is you have a very good, precision measurement of the temperature of those stages, and we can use that as an input when we're making these measurements. Does that make sense? Any questions about Y factor measurements? Okay. Another thing to consider is that you may not be able to get away with one individual amplifier. In fact, you usually cannot get away with that because typically there's some sort of trade-off between how much gain you get from your amplifier versus how much noise it's adding. So you typically want to have very low noise amplifiers close to your device, and then you have amplifiers that have more noise but larger gain sort of cascaded. And so if you're thinking about the total noise that's added, you can write it down like this. You typically write down this noise figure as referred to your input. So this is the noise temperature referred as if all of the noise was coming from your cavity itself. And then you basically divide each of these subsequent stages by their gain to sort of back propagate what that temperature is. Okay, so we know, we've been talking about all week, this signal is really, really small. And so you don't want to be, we're often going to be sort of swamped by noise, and you have to average the noise down as you enhance your signal. So what you do is you basically measure many spectra, and then you average them together, and then you can average away this random noise. Okay, and this is what it looks like in circuit diagram form. So basically you have your cavity, that's where your signal is coming from. I think this is actually this, I think the circular is backwards this direction, so I think it should be going, oh no, yeah, it is not. So you basically have this signal coming in. This is what's called a circulator. So it's a device that can move signals in one direction only. And so you basically follow the direction of the arrow. Anything coming this way will come out this port. Stuff coming in this way will come out this port, and stuff coming in this way will come out this port because of that circulation. So all of the noise, all the noise and signal from your cavity is going to be going through this circulator and going through your amplifier and then up and out. And you often put sort of layers of circulators on your signal chain. What's not drawn here is this will be shorted to the cold stage of your fridge because you don't want just thermal noise coming down your lines and entering your cavity. So all of that gets shorted out at these cold temperature stages so that it doesn't go back in. Okay, so there's multiple different sources of noise that we should consider. At these frequencies, this is what your noise actually looks like. So we have the standard quantum limit. So this is quantum noise that's added to your system. And then you also have thermal noise that's added to your system. And so you can see this is a function of the temperature. As you get really hot, thermal noise is going to be totally dominant. Okay, that's why we have to cool down, right? As you get lower, the thermal noise is going to drop below any additional quantum noise. And so that's really the thing that you're going to be wanting to reduce if you're trying to improve the signal to noise ratio of your detector. So you can see it in equations here. This is the thermal noise that you're adding, and then you have your quantum noise. Okay, so like I said, we often use parametric amplifiers in order to amplify our signal. The sort of classic example that people use is what's called a Josephson parametric amplifier. This is a narrowband device, but it's very close to or right at the standard quantum limit, where the standard quantum limit is basically adding a half photon of noise. And I'm going to talk about that also in more detail during the sort of low mass quantum sensor lecture. Okay. So I guess the thing to take away from this slide is basically it's a reflective device. So you can see here, this is an example with a qubit. You could just sub out your qubit for an axion cavity. It goes into this amplifier, and you can see we have that circulator again, and you're basically reflecting your signal off of this amplifier, and it comes out. And that's how you get the amplification. There's a bunch of stuff going on under the hood here. So what actually is parametric amplification? This is really analogous to when you're on a swing. You're pumping power in and increasing the size of your signal. And so you can imagine, so I normally swing where I'm kicking out my legs and stuff, but you can also swing where you basically are standing up and sitting down, where you're standing up and sitting down at twice the frequency that you're swinging at. And that will allow you to parametrically swing with a larger and larger amplitude, right? So you can basically just, as is very classic in physics, conjugate those variables between a mechanical system and the electrical system that we're actually using to read out our axion search. I think there was a nice figure. Yeah, so I really like this figure right here. It really explains what's going on. You're basically actively modifying the potential that you're moving within. So you can think about if you have this ball that's moving back and forth in this potential, as you're moving up the hill, the potential is more shallow, so it takes some energy to go up, but then you actively move that potential, so as you're moving back down, you're moving down a steeper slope. And so that way, you're basically enhancing the signal, and you're going to be amplifying that effect. If there's something here, yeah, okay. Are there questions on this concept for parametric amplification before I move on? Okay. Yeah, so basically you want to be shifting it back and forth at twice this frequency. So you can think if you want to go on the shallow up. So every time you're on either side of that potential, you're modifying your potential, not just one time. Yeah. And so, right, you can see in the sort of swinging example, right, you're standing up twice in the period as well. Okay. Yeah, so the result is basically that you end up with this with sidebands that you're adding to your signal. So you have a pump frequency, you have your signal frequency that gets added onto the pump frequency. So you have some gigahertz signal, and then you have sidebands that are added on. And the sidebands are the thing that you actually are interested in. Okay, let's see what here. I don't know that I want to go into this in a lot of detail. Okay, so this is what it actually looks like in real life. So any okay, so this is a traveling wave parametric amplifier. So it's similar to the JPA where you're pumping your system, but instead of only having a narrow band response, you can actually get amplification over a much larger range of frequencies. And I don't think that there's a photo of how these actually work, but basically you have these nonlinear elements in a very long transmission line. So you can have either a long line of Josephson junctions, or you can have a long line of like very narrow wires that give you kinetic inductance. And all of these things are adding nonlinearity to your system that allow you to increase your amplitude. And so this here is the response of a traveling wave parametric amplifier. And so basically what you're seeing is the gain as a function of frequency, and you pump it somewhere in the middle, and then you end up with gain on either sides of that pump. And so this is really nice when you're trying to do a wide band axion search, right? So you can either take a JPA, which has a narrow band response and only look over a narrow range of frequencies, or you can, and then swap it out, right? Or you can just use a tuba and you can amplify everything as you continue to scan. And these have really nice low noise temperatures that are very close to this limit, this standard quantum limit, where you add a half photon of additional noise. And actually, I think they just recently demonstrated the first tubas that were right at this standard quantum limit using some fancy flow K engineering. Okay, and so this is what a science run actually looks like. So you have a resonant response, and then you scan that resonant response over a range of frequencies. And so you can see each of these little peaks is a place where they have retuned the cavity, and they've sat and integrated there for a period of time. And so my guess is there was probably a mode crossing right here in the middle. And so they sort of skipped that section. As you are doing your scan, you're going to have to re-optimize the operation at each different position, or at least at every sort of so often frequency steps. And so when you're re-optimizing your tuba, you have a bunch of different parameters that you need to optimize. This is like the power of your pump, the frequency of your pump. And I think this is showing, the amount of power that you can get out of your tuba, depending on the frequency you're operating at and whatever bias pump, this is maybe a DC bias that they're adding. You can run in different modes where you add either a DC signal or an AC signal to your tuba. Okay, and so this is the science run that they did with Quacks. And so you can see, here's an example of what the data would actually look like for any different sort of single acquisition where you have that resonance frequency. And you can see that it's centered right at 10.2 gigahertz. What you're going to do is you want to get rid of this line shape because that's an effect of your detector, not an effect of the axion, right? So you can divide by the gain of your system, and then you get something that looks like this, right? So you have, you're dividing by a large number right at the middle, and then you have very wide sort of variation in your noise outside of that because your gain is lower there. And then you use this data to look for the axion signal on top of it. Let's see, what else here? Yeah, I'm not sure what all of these different pieces of data are, but yeah. Okay, and then with that, you can actually set exclusions. And so you can see there's the exclusions that they're able to set, and they're just a little bit above this KSVZ line. And so actually, this is really nice. You can see where there are things that got cut out, probably from mode crossing. So maybe this isn't a mode crossing because it's too wide. I don't know why they're not operating there. It may be something about how they've designed their cavity. And so you'll notice that this is actually not that long of a period of time, but recall again that integrating for a lot longer doesn't actually help your sensitivity very much because it only goes as the fourth root of time. And so they were able to get these really nice results in just, was that less than 10 days. So, okay. I think that's the last slide. So we're a little early, but I didn't have all the information, so. This one? Yes. And then we have a large graphic and then yeah, if you look here, it's the same. So it looks like they didn't scan that section. I don't know why they didn't scan that section. So at first I was thinking it's a mode crossing, but I actually think that the mode crossings tend to be pretty narrow. So my guess is that, I mean, maybe these are mode crossings and this is EMI. I'm not totally sure. EMI is electromagnetic interference. So they could have some source of noise that's preventing them from reading out there. So remember, like I said, we had radio stations in our DM radio data. They won't have radio stations because it's not in the gigahertz, but you have like, that's the Wi-Fi band and other things like that. So there's other signals that may be happening in their lab specifically that prevent them from looking at those frequencies. Other questions? Yeah. Yes. So for these cavities, you basically get rid of the magnetic field, and then you can have the dark photon drive these modes in the exact same way. So if you'll have an oscillating electric field basically from the dark photon mixing with the regular photon, and then you can resonantly enhance that signal. You just don't need it. You could have the magnetic field there, but then you wouldn't know if it's an axion signal or a dark photon signal if you had a result. And it's very expensive. So you could easily build a dark photon experiment with just a cavity, and you don't have to buy that expensive magnet. So that's actually a route a lot of experiments take when they're first doing something, is they'll build a dark photon experiment, show that this technique works, and then they'll add a magnet to it. Have low noise, for example, show tunability. There's lots of sort of technological things that you need to demonstrate. And in this business, not seeing a signal is still a success because otherwise we would all be failures all the time. So yeah. Mm-hmm. Mm-hmm. So there's still layers of shielding here. They're typically radiation shields. So I don't know if I can go back to the photos of the lab. Maybe it's easier to just scroll. There we go. So you can see the cavity in here. Basically, these different plates will have layers of shields that are added around it. And you need those in order to cool down so that you don't have hot room temperature photons impacting your 10 millikelvin space. But they also serve as to some extent as EMI shielding. You can do a better job with EMI shielding, filling all the different holes in the plates and things like that. And I assume that they've done some of that. Are you talking about the radio receiver? Yeah, so that one, that is specifically a telescope. So they can't, they cannot shield that or else they would have no signals, right? That's not looking for dark matter. That's looking for radio lines from the cosmos, radio astronomy. So they would not be able to see this level of small signals because they have much more backgrounds. One thing that's interesting about the Green Bank telescope, though, is it's in this National Radio Astronomy Observatory, which is this area in West Virginia in the US, which is a very rural place, and they actually ban people from using wireless nearby. So you cannot have your phone on in that area. You can't have a normal radio. You actually can't have a normal microwave there either because they emit tones at frequencies that matter. And you have to have these really old cars that don't have computers in them that are emitting things. It's a pretty interesting place. It's very back to basics kind of environment. Hmm? Yeah, yeah.
Somewhere else,
So this Green Bank telescope was not built for axions. It was built for radio astronomy generally. You can do searches for axions using their data. And so like you can look for radio lines and things like that. But it's a multi-purpose instrument. It's just an example of a radio receiver. Yeah. Yes. So that's for the JPA. For the TUPA, which is also a form of parametric amplification, it has a wider gain profile. So oh, yeah, so there. So you can see it's hard to read out, but this says span 6 gigahertz. So this is 6 gigahertz wide. And so you can amplify in these regions. It's the J2, the JPA that is more of a narrow band amplifier. This one, it still uses the same idea where it's parametric amplification, but it's a much more complicated way that it does it. It sort of does this dispersively along a transmission line. So, yeah. Yeah. That's just a great question. So the axion, you always have that method where you can ramp down the magnetic field, and that differentiates it from a dark photon, right? So a dark photon signal, if you ramp down your magnetic field, it would stay there. A gravitational wave has a different signature in frequency space. So it won't have that Maxwell-Boltzmann distribution of the standard halo model. It will have some frequency distribution that's dependent on what is actually sourcing those gravitational waves. So if you've seen like the LIGO signals, you have this in spiral, it has that chirp in frequency space. At these frequencies, you don't expect to be seeing in spiraling black holes. There's a lot of different theories out there for what could generate gravitational waves in this frequency band. It could be like a monochromatic, it could be just like one monochromatic tone, but it's much more speculative because there's no known sources that should generate those gravitational waves. It would be something new. Yeah.
So I'm not 100% sure, but I'm pretty sure like if you were to wait like the whole day, there probably are directions where it could be zero because the gravitational wave has direction and polarization. So it's a less trivial thing.
All right. And if it's a persistent source, you can make use of that. If it's a transient source, all bets are off. But yeah.